So the second part of what's bound to be three parts, we learn another way to solve a system of equations. Substitution method, it's an important method for solving systems of equations. The method that we use now in this video, the elimination method, is probably my default strategy. So the elimination method is really useful for solving systems of equations that look like these systems on the right hand page, where the x's and y's are lined up to the left of the equal sign and to the right of the equal sign is a constant. If the problem is set up like that, or if it's easy to get the problem set up so that the x's are lined up, the y's are lined up on the left hand side of the equation, I don't even have a number here, let me just make one up, and on the right side of the equation you have constants, then the elimination method is probably the method that you want to use to solve the problems. It's easier than the substitution method, at least to get started. So in the elimination method, the variables are usually lined up for me. If they're not, I'm going to line up the x's and line up the y's on the left hand side of the equation, get the numbers, the constants to the right of the equal sign. And then here's the big step. I'm going to multiply one or possibly both equations by suitable numbers so that the two equations have the same variable with opposite coefficients. This is the part that requires thought that I tried to type up. So if I'm given a system of equations, how do I decide how to transform the equations? Well, the first thing I do, one step at a time. If in a system of equations I see a variable whose coefficient can be multiplied by a single number to equal the coefficient or the opposite of the coefficient of the corresponding variable in the opposite equation, that's a mouthful. What I do is I look at all the numbers. I ask myself, the 3 in front of the x in that equation, can I multiply it by something that's not a fraction to get the 5 under it? No. The 12 in that equation for the y, can I multiply it by something to get the 6 under it? Not so nice. The reverse. The 5 in front of this x, can I multiply it by a number to equal to 3? Not really. The 6 in front of the y, can I multiply it by something to get 12? Yes. So what I'm going to do is I'm going to take the 2 that I can multiply this 6 by to get 12 and multiply the entire bottom equation by that 2. But on this step, I'm going to want the signs to be different. What I'm going to do is I'm going to multiply everything in every coefficient and constant in the bottom equation by -2. I'm going to do -2 times 5x and get -10x, -2 times +6 and get -12y, and -2 times 41 and get -82. What I've done is I've created two equations stacked on top of each other that I can add together and drop out a variable. Here, if I added these equations together, 12x plus -12x cancels, 3x plus -10x is -7x, and 33 plus -82, I didn't design these to solve, equals -49. I can get an answer for x really quickly. I'm not going to solve the problems, I'm just going to show you the thought process I am employing. This is another example, the second system of equations, where it's real easy to look at the systems of equations and find one coefficient that you can multiply by a single number to equal the opposite coefficient. And that's this -5. I could multiply this -5 by 3 to get that 15. Specifically, when I do the multiplication, I want to create equations that have opposites in front of one of the variables so I can add them together and cancel. And the best situation is look for two variables that are stacked on top of each other, that one of the variables can be multiplied by a number, an integer, just to equal the one above it, and do that multiplication to make the signs opposite. In this version right here, if I took the bottom equation and multiplied everything by 3, I can leave the top equation, 15x minus 9y equals to 10, and then in the bottom equation, 3 times minus 5x is minus 15x. 3 times positive 8y is positive 24y. 3 times 41 is 123. And what this allows me to do, it allows me to add the equations together. The 15x's will cancel. Negative 9y plus 24y gives me positive 15y. And I think these add up to 133. I have an equation that's super easy to solve for y, even though the answer might be a fraction at this point. This is the best case scenario. If you have one number, one coefficient that you can multiply by a single number to equal the coefficient above or below it, that's what I would generally do. That's my first go. If you don't have that situation, like these situations right here, if I look at the four numbers, there's something times 8 to equal the 3 below it. I don't know what that is. Something by the 3 in front of this x to equal the 8 above it. I don't know what it is. Something times the coefficient 2 of this y to equal to 5. I don't know what it is. There's no easy multiplication. There isn't, oh, 6 times 2 is 12, 5 times 3 is 15. There isn't any of that here. So if there isn't any of that here, and you have variables with opposite signs, then we're going to multiply each equation by the opposite coefficient with positives. So the y's have opposite signs. If I multiply the top equation through by 5 and the bottom equation through by 2, that's going to make both the y's have minus 10s in front of them. So if you have no clear way to multiply the top equation by the coefficient of the variable you're trying to eliminate in the bottom equation, multiply the bottom by the coefficient of the top. For this one, I can rewrite this as 40x minus 10y, going 5 times 8, 5 times minus 2, and then 5 times 38 is 190. And then the bottom equation, I do 2 times 3x, which is 6x, 2 times 5y, which is plus 10y, and then 2 times 20 is equal to 40. And this is my goal. My goal, as quickly as I can, is to do the most efficient multiplication so that I can add the system of equations together and drop out a variable. I can only drop out a variable if I create opposites in front of a variable. And I've done that here with the not such a nice way, the double multiplication way. So these are the best situations where it's one equation to multiply. This is still better than the worst it can be because the numbers in front of the y's have opposite signs. If you're given the worst situation, there's no one number I can multiply the top equation by to get a canceling. There's no one number I can multiply the bottom equation by to get a canceling. And everything has the same signs. When every coefficient has the same signs, you're going to have to multiply one equation by a negative and the other in a positive. And I'm just going to eliminate the x's. I'm going to make the x's have the same number. I'm going to multiply the top equation by 5, the bottom equation by 7. That will make both my x's have 35s in front of it. But that's not going to be good enough because I have to have opposite signs. I'm going to just tack a negative on there. And now I'll get what I need by doing negative 5 times positive 7x, which is negative 35x. Negative 5 times negative 4y is plus 20y. Negative 5 times positive 6 is negative 30. And then positive 7 times positive 5x is positive 35x. Positive 7 times minus 7y is minus 49y. Positive 7 times minus 4 is minus 28. Just like I've done in each of the problems on this page, I've done the least amount of algebra possible to make it so I can add the equations together and drop out a variable. So there's three levels of difficulty. You multiply by one number, you multiply both equations by positive numbers, you multiply one equation by a negative number, you multiply another equation by a positive number. This is all that can happen in this section. So this is the preliminary. Now we can jump into the work. So if I was doing problem 2, my steps for solving by the elimination method, first say to line up the variables. They're lined up already. I think they're going to be lined up for all of us. This step is done in all, if not most, of the problems. Now I'm going to figure out what variable I want to drop out. My preference is to do one multiplication with a positive. And if I look at the coefficients of the y's, this y has a 1 in front of it, that y has a negative 3 in front of it. I know 1 times 3 is 3, and not having to multiply by negatives is a good thing. I have two choices in problem 22. I can multiply the bottom equation by 3 and cancel out the y's, or I can multiply the bottom equation by negative 2 and make this x a negative 4x to cancel with that positive 4x. Both are fine. I don't prefer to multiply by negatives, so I'm going to multiply the bottom equation through by 3. So my first step, I'm multiplying the bottom equation by 3. This is technically my step 2, but step 1 was already done for me. I'm leaving the top equation unchanged, and I'm going to change the bottom equation to 6x plus 3y equals to 30, multiplying 3 times 2, 3 times 1, and 3 times 10. That's the end of step 2. Step 3 is to add the equations together. This is going to give me 10x. The 3y's cancel, equal to 40. That's the end of step 3. Step 4, solve this equation. That gives me x equal to 4. I had written down that answer already. Now, step 5, this is the bad part of this. I have to use substitution to get the other variable, and I have too much freedom. I need to pick an equation, either equation from the beginning, and substitute. So what I'm going to do for my step 5, it doesn't matter which equation I use, but I don't have a nice equation. I'm going to use the equation 2x plus y equal to 10. I'm going to substitute 4 in for the x, and I'm going to solve for y. So I'm going to go 2 times 4 plus y equals to 10. This gives me 8 plus y equal to 10. I minus 8 minus 8, and I get y equal to 2. So for my answer, x is 4, y is 2. This will check because I checked it off screen before I started. And you notice I didn't get so formal with the steps. These are just kind of a structure, and I'll follow that structure, but I don't think I need to say this step, this step, this step. It's just kind of a process. So for problem 24, the step 1's usually done. The variables are lined up. My preference is just to do one multiplication, and I look at the coefficient, this coefficient of 2, I can multiply it by 3 to cancel out that 6. If you wanted to, that's not the only way to do this. You can multiply the top by 7, the bottom by 2, and cancel out the y's. So the path that you take doesn't have to be the same as mine. I prefer doing one multiplication as opposed to 2. I prefer multiplying by positives as well. But my hunch would be, because this 2, I can multiply by 3 to cancel out that 6x if I get a negative in front of it. That's what my choice is going to be. I like to do one multiplication, and because the number in front of this x times 3 equals the number in front of that x, I can clear out the x's with one multiplication. If I wanted to clear out the y's, I'd have to do 2 multiplications because there's no nice number times 2 to give me 7. So I'm going to multiply the bottom equation through by negative 3 to force my x's to cancel out. I'm going to leave the top equation, 6x plus 2y equals to 26. And then in the bottom, I'm going to go negative 3 times positive 2x is negative 6x. Negative 3 times negative 7y is positive 21y. And negative 3 times 24 is negative 72, if I didn't mess up. So with one multiplication, I was able to make the x's cancel. I'm going to add the y's and get 23y. And then 26 plus negative 72, or 26 minus 72, is negative 46. And then divide by 23, divide by 23, gives me y equals to negative 2. So this is the steps, but not showing the steps in so much detail because I think they're almost kind of clunky to try to do it one step at a time. Variables are lined up. I multiplied so I could cancel out the x's. added the equations together, solved for y. Now it's a matter of substituting. I don't like substituting in the negative, so I'm going to substitute into the top. So I'm going to substitute y equal to -2 into the top equation, but quite honestly, I could have plugged it into the bottom equation. It doesn't matter which equation you plug it into, you'll get the same answer. I just work better with positives. So I'm going to go 6x plus 2 times -2 equal to 26. You could have done this. You could have said it's 2x minus 7 times -2 equals to 24. You could have substituted into the bottom equation and get exactly the same answer. This way gives me 6x minus 4 equals to 26. I add 4 to both sides and get 6x equals to 30. And divide by 6 and get y equal to 5. This guy, if I had done the other substitution, I'd still get the same answer. So it doesn't matter. Doesn't matter even on the first step. If you decided to eliminate the y's because that looked easier to you, you'd get the same answer. Your algebra could look shockingly different, but it should still work. Next problem, I almost deleted it. I didn't want to work with a fraction, but I figured, what the heck, let's work with a fraction. We got a calculator. So what am I going to do? I look at the coefficients. 3 times what equal to 4? Nothing good. 4 times what equal to 3? Nothing good. 2 times what equals to 5? 5 times what equal to 2? I can't think of a single number that I can multiply by to cancel out a variable. When that happens, I need to multiply both equations by the opposite coefficient, and I love opposite signs. When I have opposite signs, I don't need to multiply by a negative. So I'm going to multiply the top equation by the number in front of the y in the bottom, and the bottom equation by the number in front of the y in the top. So when there isn't a single multiplication I can do, I just multiply by the opposite coefficients. And when the signs are different, I don't need to multiply by a negative. They already have the opposite signs for me. So let me do the top by 5. So 5 times 4x is 20x. 5 times 2y is plus 10y. 5 times 3 equals to 15. Bottom by 2. 2 times 3x is 6x. 2 times minus 5 is minus 10y. 2 times 1 is 2. Add these together. 20x plus 6x is 26x. I cancel the y's. 15 plus 2 is 17. Divide by 26. Divide by 26. X equals 17 over 26. By hand, I wouldn't even make a shot at this, but with a calculator, not such a big deal. Now I need to take this answer and plug it into either equation. I prefer working with the positives. I'm going to plug it into the top equation. So I'm going to use the equation 4x plus 2y equals to 3, and I'm going to sub in x equals 17 over 26. And I'm going to work the heck out of my calculator. First, I'm going to do 4 times 17 divided by 26. Math, enter, enter. This gives me 34 over 13 plus 2y equals to 3. And so now minus 34 over 13 minus 34 over 13. On the left side, I get 2y. On the right side, I get 3 minus 34 divided by 13. Math, enter, enter, equals 5 over 13. And instead of dividing by 2, I'm going to multiply by 1/2. Heck, I'll divide by 2. I'm going to go divide by 2, divide by 2. And on the right side, I'll do the divide by 2 like that. On the left-hand side, I get my y. On the right-hand side, it's 5 divided by 13 divided by 2. Math and enter twice. 5 over 26. Mindlessly pressing buttons. I don't do fraction answers on the test unless I make a mistake and I didn't want the answer to be a fraction and it accidentally works out to be one. So it is what it is, but they're doable. Problem 28, I had to change to get the answer of 6-4. Let's do problem 27 that I don't know the answer for. In problem 27, I'm going to get rid of the fractions by multiplying the top equation by 4. So in 27, I'm going to go 4 times 2/4 x plus 4 times 1/2 y equals 4 times 2. Fractions aren't my friend for these problems. If I get a problem with a fraction, I get rid of the fraction on the first step. So first is 4 times 2/4, which is going to give me 2 in front of the x. And then 4 times 1/2 is going to give me 2 in front of the y. And then 4 times 2 equals to 8. And I'm going to leave the bottom equation. So I'm going to have 2x plus 2y equals to 8. And x minus, I'm going to emphasize 1y equal to 4. Well, this is going to be good, I think. It looks to me like it's easier to cancel out the y's because they have opposite signs, and I can do it in one multiplication. If I multiply the whole bottom row by 2, that's going to get the numbers in front of the y's the same. Anytime I could do one multiplication, it's the best. Anytime I could do one positive multiplication is better than doing a negative multiplication. The number in front of this y times 2 equals the y above it, and the signs are already going to be opposite. So that's what I'm going to do. I'm going to leave the top equation, 2x plus 2y equals to 8. So we are doing 27. And the bottom equation, I'll go 2 times x is 2x, 2 times minus 1y is minus 2y, and 2 times 4 is 8. When I add these together, the y's cancel. I get 4x equals to 16. Divide by 4, divide by 4. That's going to give me x equal to 4. I need to solve for y. I don't like using negatives, but boy, this equation is appealing. So I'm going to use this to solve for y. I'm going to go 4 minus 1y equals to 4, minus 4 minus 4. That gives me minus 1y equals to 0, divided by minus 1, divided by minus 1. Fractions with 0 in the numerator are equal to 0. So the answer to this is x equal to 4, y equal to 0. That's not a no solution because the variable didn't drop out. That's just getting an answer of 0. I can check this. Again, it just takes the time that I don't know that I have so much. So let us just keep mushing along or going forward. It's going to be another 35-minute video. I'll do problem 30. I want to clear the fractions by multiplying through by the least common denominator of 7 and 3, which is 21. So in the top equation, I'm going to go 21 times 4/7 x plus 21 times 1/3 y equals 21 times 5. So 21 times 4 divided by 7 is going to give me 12x. And then 21 times 1 divided by 3 plus 7y equals 21 times 5 equals 105. I'm going to leave the bottom equation in number 30 as x minus, emphasize the 1 in front of the y, x minus 1y equals to 4. With one multiplication, I could get the y's to have the same coefficients, and I don't have to multiply by a negative. Better to get the y's to have positive and negative 7y than it would be to get the x's to have negative and positive 12x, because I can do this by multiplying by a positive. So I'm going to multiply the bottom equation by 7. I'm going to get 12x plus 7y equals 105, and then 7x, 7 times x, 7 times minus y, and 7 times 4 to get 7x minus 7y equals 128. I think this gives me 19x equals 133, and then divide by 19, divide by 19, and I get x equal to 7. I need to solve for y, and again, I don't like using negatives, but that equation is so appealing. So now as I solve for y, I'm going to use x minus, I'll emphasize, 1y equals to 4 and plug 7 in for x. So I get 7 minus 1y equals to 4. Minus 7 gives me minus 1y equals minus 3. And then divide by minus 1, divide by minus 1. That gives me y equal to 3. And I already checked that off screen. The next 3 problems before the video is going to end, we have no solutions or infinitely many solutions. You get no solutions if the variables drop out and you have a false statement. You get infinitely many solutions if the variables drop out and you get a true statement. On the next 3 problems, all the x's and y's are going to cancel. And I'm going to be left with either a false statement, and then I'd say no solution or inconsistent, or a true statement, and then I have to write my answer in that fancy form. So in problem 32, it turns out that if I decide to drop out the x's, I'm also going to drop out the y's. If I try to drop out the y's, I'm going to also drop out the x's. So I look at problem 32, it looks to me like it's going to be easy to cancel out the x's. If I just multiply the top equation to get a minus 3 in front of the x, I can cancel the x's with one multiplication. I'm going to multiply the top equation by negative 3. That will make the x's cancel and, unfortunately, the y's. So I'm going to go minus 3 times positive 1x in the top equation and get negative 3x. Minus 3 times minus 3y and get positive 9y. And then minus 3 times positive 7 and get minus 21. I can leave the bottom equation as positive 3x minus 9y equals to 4. And simultaneously on the left-hand side, both the x's and the y's cancel. Once both the variables cancel, there's no real more algebra that you can do other than possibly writing a solution in a nice way. Here, all the variables dropped out, a false statement remains, there's no answer. If I graph these would be parallel lines that don't cross. So there's no solution to problem 32. I imagine 31 is similar. 34, on the other hand, it's going to have infinitely many solutions, which means, because I can tell by the answer that I wrote, it means all the variables are going to drop out and a true statement's going to remain. So let's get into that part right now. So I can drop out the x's or drop out the y's. They're going to both drop out. I'm going to pretend like I'm trying to drop out the y's. I'm going to multiply the top equation by 3. That's going to give me a 6y to cancel with the negative 6y. So I could do it with one multiplication because the coefficient of this y times 3 equals the coefficient of that y. Better yet, with opposite signs. So top equation by 3. 3 times 6x is 18x. 3 times positive 2y, positive 6y. 3 times positive 3 equals 9. Leave the bottom equation minus 18x minus 6y equals minus 9. Left hand side, both the x's and y's cancel. Right hand side, both the numbers, the 9's cancel. If all the variables drop out and you're left with a true statement, you need to pick an equation, solve it for y, and put it in this shell. And there's my shell, but how do I get that shell? I pick an equation now. So if all the variables drop out and you get a true statement, that means if you graph the equations, they graph right on top of each other. They're the same line. So I'm going to pick the top equation and solve it for y. Because my instructions say if the variables drop out and I get a true solution, pick an equation and solve it for y. That equation has a lot more positives in it. It looks easier to work with. So to solve this for y, I'm going to minus 6x and minus 6x and get 2y equals minus 6x plus 3, and then divide by 2, divide by 2, divide by 2, and get y equals minus 3x plus 3 halves. You could write 1.5 for it. What I did is I used this shell right here, took everything from this shell and duplicated it, except I put the equation solve for y. Everything else that I wrote is just, that's the proper way to write an answer that has infinitely many solutions, when the lines would graph to be the same line, when any point on a line is a solution to both. One more and we'll move on to our part 3. Same deal here. This is going to have infinitely many solutions, which means all the variables will drop out and I'll get a true statement. My goal is I'm going to drop out these x's and I'm going to multiply to force the x's to cancel. The x's have the same signs. I need them to have opposite signs. If I just multiplied by 5, I can get them to have the same coefficient, but it wouldn't have opposite signs, so I'm going to multiply the top by -5. When I multiply through the top equation by -5, I go -5 times 1x and get -5x, -5 times -2y and get +10y, and then -5 times +3 equals to -15. I'm going to leave the bottom equation alone. And just like in the last problem, everything cancels not so nicely. Or so nicely, but in a bad way. If I had like 0 equal to 7, I could just say no solution. But 0 equals to 0 means I need to pick an equation and solve for y. It doesn't matter which equation, but if you solve it for y and simplify, they'll come out the same. I'll pick the equation with the smaller numbers because all the y's are negative. And I'm going to get fancy here-ish. So to solve this equation for y, the y having a negative in front of it is going to doom my algebra. I'm going to make the y have a positive in front of it. Even though I'm getting the y on the right-hand side, which is weird, I'd rather have the y on a weird side than have a negative in front of it. So my first step is just to get rid of the biggest issue I was going to have. And the biggest issue I was going to have is having a negative in front of the y. It's going to make it so hard to match up with my answer. And now I'm going to divide through by 2. And then I could write either 1x over 2 minus 3 halves equals to y. And this x can be drawn out front. It'd be equivalently okay to say 1/2 x minus 3y minus 3 halves equal to y. And this guy right there, I could have even written it as x over 2 minus 3 halves equal to y. All 3 of these are considered solved for y. All 3 of these could go in the shell of my answer with the y first. And I picked this one because that's kind of the most common way to do it. So I took my algebra and solved for y, wrote it with the y on the left-hand side because that's what I'm used to, and just drug out this shell. Again, I never put this on the test for this. I don't have, there's enough in this chapter that this isn't such an important skill that I test on it. But I want you exposed to it. You should definitely be aware of it just in case you take some other class that has systems of equations like Math 218 and you run into something like this. All right, there's still a third part, so we'll get to it here in a minute.